very nice to be here. My talk will be on a completely different subject, entirely unrelated. It's going to be about revisiting some old puzzles about how to think about baryons in quantum chromodynamics. So there will be some connections to both real-life physics, as well as some theoretical developments about Yang-Mills theory and quantum chromodynamics. Okay, so the setup is going to be, and also if there are any questions, please stop me at any. I might not finish everything I gotta say, but it's okay. So the setup is just QCD. It's an SUN gauge theory with an F quarks. In the fundamental and anti-fundamental representations, the usual Dirac quarks, and there is a mass. And also in this talk, I'll put theta to 0. So I won't discuss the QCD theta parameter. Okay, so this is the theory. And as is well known, this theory has SUNF times SUNF symmetry, which is sometimes called isospin symmetry. And there is also U1 baryon symmetry, which acts on these quarks in this way.
All the masses are equal?
Yeah, and I'm going to take all the masses to be equal for simplicity, so that there is an isospin symmetry. And furthermore, the most interesting regime of the theory is, of course, when the masses are small and the theory is strongly interacting. There are large fluctuations, and the baryons are interesting, and also the mesons are interesting quantum objects rather than just classical objects. So, of course, everybody knows that there are two types of excitations, namely those that are charged under baryon number symmetry, which are called baryons, and then there are mesons. And there are also gluons, which I didn't write here explicitly. Okay, so let me just make some simple remarks. So the excitations that are created from the vacuum by acting with fermion bilinears, those are the mesons. And the lightest mesons in QCD are these pseudo-Nambu-Goldstone bosons, namely the pions and kaons, which arise due to the spontaneous breaking of the approximate chiral symmetry. So that's what you get if you act on the vacuum with bilinears. And then there are excitations that are created by acting with the baryon operators, and they lead to the baryons, to the proton, the neutron. And now it would be useful for some point much later on in this talk to remember the representation theory of the baryons. So the baryons have to be completely symmetric in the spin and isospin quantum numbers, since they are completely anti-symmetric in color. So they have to be in this power n symmetric representation of the fundamental representation of spin times the fundamental representation of isospin. That will be important for some things at the end. And so, for instance, if you plug n equals 3, which represents a normal QCD, then you get baryons in the octet and the decoupled representation. The baryons in the octet have a spin 1/2. Those are the proton, the neutron. And the baryons in the decoupled have spin 3/2 and include the delta particle, the famous delta baryon, and also the Israeli omega minus baryon. Okay, so this talk is really about the duality. It's about a small puzzle about duality. That's what it's about. The duality is due to a 't Hooft. 't Hooft said that in the infinite n limit of quantum chromodynamics, quantum chromodynamics is equivalent to a completely different thing. It's equivalent to infinitely many weakly coupled massive particles. So there is no gauge symmetry in this description. This is one of the first instances of duality. Of course, it's a precursor for ADS-CFT. And this talk is about a puzzle in this duality. If you look at the papers of 't Hooft and all the other, many of the following papers, there is a question about where are the baryons in this duality. The duality of 't Hooft was that infinite n QCD is equivalent to the Lagrangian of pions, kaons, and many other mesons and gluons. Infinitely many, in fact. So it's a duality between an ordinary quantum field theory in the large n limit and a quantum field theory with infinitely many fields, like a string field theory a little bit. So people have asked, where are the baryons in this duality? That's a question that, as far as I know, was perhaps first posed by Witten. At least the first paper that I saw about it is due to Witten. And the answer was the following. The answer was that in the large n limit, the baryons are very heavy, since they consist of n quarks. And since the coupling constant is 1/n, h bar effectively in this duality of 't Hooft, the weak coupling parameter in this side of the duality is 1/n. And since the baryons are expected to be heavy, you can think about their mass as being 1 over h bar. And therefore, the suggestion was that baryons should be viewed as collective excitations of the mesons and gluons, namely as solitons. Now, this description of baryons as solitons might not be terribly practically useful, because we have infinitely many fields on this side of the duality. So constructing solitons of a classical field theory with infinitely many fields is not a terribly practical task. But one is lucky, because one can construct solitons just out of finitely many of these infinitely many fields, and that's more useful. And there was, of course, a huge amount of work on these solitons. So let me just review how it works, and then I'll tell you what's the puzzle. I haven't told you the puzzle yet. So one focuses one's attention on the pseudo-Nambu-Goldstone bosons, which are these matrices SU and F matrices U. Those are the pseudo-Nambu-Goldstones which consist of the pions and kaons. And the parameter n appears as a coupling constant in this approximation. So when you take the large n limit, this theory of pions and kaons becomes extremely weakly coupled. And the main idea was that you can create solitons out of these fields, which represent baryons, classical solutions that represent baryons. And there is a topological argument for that. One relies on the third homotopy group of SU and F, which is given by the integers, or equivalently, there is a conserved current, which is tautologically conserved. It's called the topological conserved symmetry sometimes, or topological symmetry, or skyrmion symmetry. And this conserved current is supposed to represent the baryon density. There is a small thing that I've not said, which will be important later on, but for now it's not, which is that in fact these matrices U are not SU and F matrices. These matrices U are actually U and F matrices, because there is a light eta prime particle in the large n limit, but that makes no difference because it decouples from this formula anyway. So the U1 part of the group manifold doesn't make a difference. It decouples from this formula. In other words, pi3 of U and F or SU and F is the same thing. So physically, small excitations of this U field they describe pions and kaons, while excitations of the U field which have some topology and lead to a non-zero integral of J naught, they describe baryons. And there's a huge amount of literature on these baryons. People have studied how to write these baryons explicitly, what do they mean phenomenologically, and so on. I also made some comments here about the typical size of the baryon, but I'm going to skip it in the interest of trying to get somewhere. So there are some technical remarks on the fact that to actually write down consistent soliton solutions, you need to add some higher derivative terms to this classical field theory. And so this is an important fact, but I won't explain it here. It's not important enough. So let me get to the puzzle which motivated me to look at this subject again. The puzzle is that this whole edifice completely collapses for an f equals 1. So on the one hand, there are still baryons on the left-hand side of the duality. So in this duality, there are still baryons on this side of the duality, but there are no baryons on this side, at least not naively. However, the usual construction of baryons on the right-hand side of the duality collapses for n f equals 1. It doesn't work. That's because pi3 of U1 vanishes. So this formula for the baryon density that I've given you here, this formula becomes trivial if the matrix is just a U1 matrix. You can just plug a U1 matrix and it just identically vanishes. It's obvious. So there is a small puzzle about the duality, and that's why I decided to revisit this question. One can ask, how do we identify baryons on the right-hand side of the duality, of 't Hooft's duality? Is there a useful way to think about solitons that are made out of globals and mesons that would lead to baryons for one flavor QCD? Now, an important fact is that in one flavor QCD, there is just one baryon. The representation theory simplifies. There is one baryon which has a high spin, n over 2. So if there is a solution to this question, it would probably also pertain to certain questions about QCD with more than one flavor, because it might be relevant for high spin baryons. So what I'm going to discuss today is not limited to one flavor QCD, even though that's what I'm going to do for simplicity. So the question is, where is this high spin baryon hiding on the right-hand side of the duality? So let's try to understand. Let's try to solve this question. Let's see what ingredients are necessary to try to attack this question. Of course, this question might be important phenomenologically, because if one can come up with a useful description for this high-spin baryon, it might say something about the delta baryon, for instance, even in real-life QCD. So when we have one flavor in an f equals 1 QCD, this is the effective field theory. We just have one U1 pseudo-Nambu-Goldstone boson, which is called the eta prime particle, and that's the effective action. It has a kinetic term and some potential cosine due to the mass of the underlying quark. And this is assumed to be a very small parameter. So we have a small cosine potential on a circle. This theory has some interesting property which you might not have seen before if you haven't followed some very recent literature, which is that this theory has a weird conserved current with 3 indices. And this current is conserved regardless of these corrections here in the dots. So this is an approximation to the low energy effective action of the eta prime particle, but there are infinitely many corrections with more derivative and more complicated potentials. But whatever you write here is going to be invariant. Whatever you write here would not destroy this current. So this conserved current is sometimes called the two-form U1 symmetry, and it does not act on particles. It acts on certain domain walls made out of the eta prime particle, which I'll explain. It's, however, a little bit weird that this is a symmetry that cannot be broken by higher dimensional operators. Like, you might be used to baryon number in the standard model, which is broken by a higher dimensional operator. But this particular kind of symmetry cannot be broken by any higher dimensional operator. However, it's not a symmetry of QCD. There is no such symmetry with 3 indices in the full QCD model. So even though it cannot be broken by any higher dimensional operator, it's not a symmetry. The most important thing is that the excitations which carry this symmetry, yes?
Wait, you said it acts on domain walls.
Yeah, because it has 3 indices and it's antisymmetric in those indices. So it doesn't act on particles.
How do we know there isn't such a thing in QCD?
Well, you cannot write a conserved current with 3 indices using the fundamental degrees of freedom of QCD, using the gauge fields and the quarks.
We could dualize that and then we just have one index.
That's right, but in the dual description, the conservation equation prefers like one particular convention. We want the conservation equation to act like a divergence, right? So currents which have 3 indices and are antisymmetric in these 3 indices do not act on point particles. They act on world volumes which are 2 + 1 dimensional. Sometimes people call them domain walls, but it's misleading. I won't call them domain walls, I'll call them sheets. And sorry if my pronunciation is not perfect. So
Sorry, Zohar, does eta prime, what's the target space? I mean, because,
eta prime lives on a circle.
oh, okay, because otherwise this is just trivial.
That's right. If eta prime was a non-compact real scalar, then this would be an empty object. It would not act on anything. It would be just like a, it would never integrate to something interesting.
Yeah.
And since eta prime lives on a circle, it's a U1 group manifold. This theory admits certain objects which are 2 + 1 dimensional world volumes. And the consequence of the fact that this symmetry cannot be broken to any order in perturbation theory means that these sheets are going to be extremely long-lived. So their lifetime is an exponential of n, where n is the number of colors. So we're saying that in QCD, there are some extremely long-lived 2 + 1 dimensional world volumes that are made out of some codimension 1 objects in space-time through which the eta prime goes around the circle. So it's like it's like an interface between two sides of space, and if you cross the interface, eta prime goes around the circle. So you can ask, what is the world volume theory on this object? And the world volume theory is, of course, the Nambu-Goto action, because these things break spontaneously translational invariance. So we just have the usual action that you see for in string theory on the D2 branes. You can also imagine that these things have a boundary. You can take such a sheet and have a boundary. So if you go through this direction, you don't have a monodromy. But if you go through this direction, you do have a monodromy. Such boundaries might be created spontaneously from the vacuum, because this sheet is not infinitely long-lived. It's only finitely long-lived. So there is a small probability that the boundary would be created. Anyway, so these sheets have nothing to do at face value with these baryons, with the puzzle about baryons, because I'm still just using eta prime, and there are no baryons here. There is no baryon number density. The key thing comes from the fact that this effective field theory is actually misleading. So even though this is the effective field theory that many people use in the phenomenology of the eta prime particle, it's not entirely correct. There is a correction to this effective field theory at the next order in the 1/n expansion. So this comes from the disk diagram, and this would come from, let's say, well, it essentially comes from the torus diagram. So there is a correction which is smaller in n, which is slightly non-analytic. So there is a correction to the potential of this particle that lives on a circle, which is slightly non-analytic. So it's a smooth function, but it's non-differentiable at one point. And the whole point of this talk is to try to understand the consequences of this non-differentiable point for these extended objects, the sheets. This is the challenge here. So our derivation of the effective field theory on the sheet, which was just the Nambu-Goto action, was not convincing because the effective field theory on the sheet is slightly singular. There is a point where the derivative is not continuous. You know from Seiberg-Witten theory, for instance, that when there is a singularity in the effective theory, it might suggest that some heavy degrees of freedom were not properly integrated out, or in fact, there might not be even heavy. Here, the singularity is not as severe as in the Coulomb branch of Seiberg-Witten theory. This singularity is still smooth, but non-differentiable. So our interpretation of this singularity is that some heavy fields, which were integrated out improperly, meaning that some heavy fields have in fact two equivalent vacua that they could choose, and our effective field theory does not take that properly into account. So some heavy fields could be jumping from one gapped vacuum to another, and the idea is that this is what this singularity reflects. So mostly people study small fluctuations of the eta prime particle because they want to do phenomenology of mesons, and so they completely ignore this singularity, because this singularity occurs at eta prime equals pi, which is away from the vacuum, which is eta prime equals 0. But if you want to study these extended objects more seriously, these extended 2 + 1 dimensional world volumes, if you want to study them more seriously, you must think about it. Because once you go through the sheet, in this picture, if you go through the sheet, eta prime goes all around the circle, and in particular, it swaps also around this. It also goes around this point, eta prime equals pi. So you have no choice but to try to understand what the singularity means. A useful guide for understanding what the singularity would imply is actually two-dimensional field theory. Those of you who know two-dimensional field theories have already seen this precise kind of singularity before. So now I'm going to spend like a few minutes just explaining some well-known two-dimensional physics, but you will see that it leads to a very concrete picture for what we're supposed to do about the singularity. So the analogy with two dimensions here is very useful. So consider two-dimensional U1 gauge theory coupled to some heavy scalar fields. So I'm imagining something like scalar QED, where the scalar field is very heavy. So there is a kinetic term for the gauge field, a theta parameter for the gauge field. There is a theta parameter in 2D, which I'm going to keep for a while. And then there is the coupling between the gauge field A and some massive dynamical charged scalar fields. Now, this theory has approximate energy eigenstates where the electric field, okay, so classically, let's start from the classical physics. Classically, the equations of motion in 2 dimensions mean that the electric field is just constant unless there are sources. So in the quantum theory, since the scalar fields are massive, the ones that are hiding in this current, then there are energy eigenstates, which represent states with approximately constant electric field. And the electric field is given by an integer modulo theta. So, sorry, the electric field plus theta is an integer. These are approximate energy eigenstates of 2-dimensional QED with some heavy matter fields. And the energy of these approximate eigenstates are given by this thing. I think that this might appear also in Nari's talk. Yes, this formula. So if theta is not pi, there is one vacuum in 2-dimensional electrodynamics. But if theta is pi, then there are 2 vacua in massive electrodynamics in 2 dimensions. And these vacua have constant electric field. So these are only approximate energy eigenstates because I have dynamical charged particles. If there were no dynamical charged particles, this would be the exact eigenstates of electrodynamics in 2 dimensions. But the massive charged particles, they act like domain walls. There are codimension 1 particles that connect states where the electric field is E and states where the electric field is E plus 1. So they connect different energy eigenstates, and therefore they allow for non-trivial matrix elements between these energy eigenstates, and that's why these energy eigenstates are not really eigenstates. They're only approximately eigenstates. Now, the interesting thing is to add an eta prime particle. So now, if we add an eta prime, we'll see some really nice analogy with the four-dimensional story. Let's put theta to 0 for simplicity, so that we have one vacuum where the electric field vanishes, as simple as it could be. And then we add an eta prime particle that couples to this electromagnetic field in this way. So it's like an axion. Now, it's a well-known exercise to try to integrate out A. And this naively generates this effective field theory for the eta prime. And miraculously, you see the exact same formula that appeared in 4 dimensions. So you get the exact same kind of function, which is continuous but not differentiable. So, and here we can really see where the mistake was. The mistake was that we were integrating out a heavy gauge field, or a gauge field, but this gauge field has two vacua at eta prime equals pi. These two vacua are the electric field is a half and minus a half. These two vacua are degenerate, and we integrated it out incorrectly. So we really see that this kind of singularity arises from integrating out incorrectly a heavy field with two degenerate ground states. And the formulas look exactly the same as in 4 dimensions. In fact, this formula is exactly the same as what we had in 4 dimensions here when you combine this and that. Okay, let's continue. We can say much more. We can ask, what happens if we consider the analog of this sheet? It's a point in space around it that if you cross this point in space, eta prime would go around the circle. This is called the kink in 2-dimensional physics. So from this formula, you see that the kink has electric charge. In fact, this is the current, which couples to the electromagnetic field, and therefore, when there is a kink, it carries electric charge. So a point in space where eta prime goes around the circle is like a domain is like a charged particle. It separates this state from this state. So we see that the heavy charged particle and the kink for the eta prime are very similar. So suppose we have such a kink for the eta prime. It's a codimension 1 region in space through which eta prime goes around the circle. Then if this is the vacuum, this would not be the vacuum. This would be some excited state. So we need to lower the energy. So what would the system do? The system would pop another charge -1 scalar, or an anti-kink, and then there will be a true vacuum here, but in the middle there is a confining string, so you get some meson. So the message here is the following. The message here is that through this codimension 1 object in space, around where eta prime undergoes a monodromy on the circle, the vacuum on the right and the vacuum to the right and the vacuum to the left are not exactly the same. The vacuum to the right has a higher energy density, and we need to cancel it by adding another object that would lower the energy density. So that's what 2-dimensional physics teaches us. And in fact, these objects are very important in quantum electrodynamics in 2 dimensions. If there is some kind of global symmetry, then they would that protects some mesons. That would be the representation of these mesons. So these kind of states are very important, and they're physical. Let me now tell you how this works in 4 dimensions and how this singularity modifies the sheet. So in 4 dimensions, we see that the effect of the singularity, it's entirely analogous. The effect of this singularity is that on one side of the sheet, like let's say up, the vacuum has a wrong energy density. It's slightly excited. So we need to lower it by adding another object that would bring it back to the ground state, like we did in 2D. So we need to understand what is the 4-dimensional analog of a charge 1 particle that could bring the energy down again and fix the energy density. And this is something that people have studied recently. In 4 dimensions, the analog of this energy eigenstates where the electric field is 1, 2, 3 are this called instanton vacua, where there is an instanton density. And it's known that there is an object in Yang-Mills theory. This is a property of pure Yang-Mills theory, that there are these instanton vacua. It has nothing to do with eta prime. It's known that there is a domain wall which allows to interpolate between vacua with different instanton density. And then this domain wall has a Chern-Simons theory living on it with an emergent U1 gauge field. So this is something that has been discussed in lots of recent literature that I don't have time to properly explain, but it's a well-defined statement that I'll use. The statement is that just in pure Yang-Mills theory, it's not QCD, there are states which are analogous to these states where the electric field is 1, 2, 3. They are called instanton vacua. And to go from one to the other, you need to put a Chern-Simons theory in a 2 + 1 dimensional world volume. And this Chern-Simons theory has an emergent gauge field A. And the level of the Chern-Simons theory is n. So now it's very clear what to do. We need to do the exact same thing as what we did in 2 dimensions, which is to combine the eta prime defect together with this new domain world that has a Chern-Simons term. And this combined object would now properly interpolate between the true vacuum of QCD and another copy of the true vacuum of QCD. So combining these objects would lead to this effective field theory. Or so a way to rephrase what I'm saying here is that the effect of the singularity of the eta prime particle is that the effective field theory on the sheet is not as simple as you thought. It's not just the phonons due to the translational symmetry breaking. It also includes the Chern-Simons term. And we've seen that the origin of this Chern-Simons term is essentially from another domain wall that lives purely in the closed string sector that comes close to the original domain wall. And it makes a lot of sense to conjecture that this is still very long-lived because this belongs to the open string sector and this belongs to the closed string sector. This comes from the closed strings part of the theory, the globals, and this comes from the open strings, the eta prime defect. So it's very natural to conjecture that this is still very long-lived and such domain walls actually exist in QCD. And so the effect of this singularity is to introduce a Chern-Simons term with an emergent gauge field. That's the punchline. That still has nothing to do with baryons, but now the baryons will come. Now, this is something that I have to attribute to Juan Maldacena, who explained to me that this analogy with 2D is basically precise in ADS. So all these things that I've told you can be seen explicitly in the Witten-Sakai-Sugimoto model, where there is a certain construction, and some ongoing work by these authors shows that this is really true. So all this conjecture is really true in ADS CFT, and there are such objects in QCD. There are such domain walls which are very long-lived, and they have this effective field theory. So the benefit of having this whole huge detour from the puzzle about baryons to these domain walls or long-lived sheets is that we can now finally describe objects with baryon number, which we could not do just with an eta prime particle. So we can now couple the baryon number symmetry. We can now define baryon number symmetry in terms of this emergent gauge field A, such that the baryon gauge field, the classical gauge field that couples to the baryon current, couples to A in this fashion. So now we have finally a way to interpret baryons through this, starting from this domain wall, because on this domain wall there are certain emergent gauge fields, and excitations of these emergent gauge fields can carry baryon number.
To be clear, A is a background field here.
Capital A is background, and and lowercase a is a dynamical U1 gauge field.
You're really just defining the current here.
Yes, I should have perhaps written it more clearly. Erase this thing and say J baryon. I can write it here. J of baryon. The current for baryons is just epsilon mu rho dA. And maybe some 2 pi. So that's the statement. The statement is that using these objects, we can now start talking about baryons. But as you see, they involve not just the eta prime meson, but also some globals, or a residual effect from globals. So we have to get back to the question of what happens if there is a boundary, like we had in this picture before. What happens when there is a boundary? Because this object is only very long-lived, it's not absolutely stable, so boundaries will be created. And as you may know, Chern-Simons theory in the presence of a boundary is very interesting. Chern-Simons theory in the bulk is a topological field theory, but once you have a boundary, there might be, or there must be, actual light degrees of freedom, which are propagating. So we need to define we need to say what are the boundary conditions, and there's a very natural answer. In fact, if you know the fractional quantum Hall effect, baryon number here in this story plays a very similar role to electromagnetism in the fractional quantum Hall effect. So let me just jump to the answer. The answer is that we impose these boundary conditions for this emergent gauge field when there are boundaries. And unlike in Chern-Simons theory, where this parameter v is not fixed, here we must take v to be 1. So that's different a little bit from the literature on Chern-Simons theory on the disk, which usually takes v to vanish. But here we must take v to be 1 because we must preserve relativistic invariance on the boundary. So that's the only choice that's consistent with the boost symmetry. Okay, so one has to quantize Chern-Simons theory on the disk with some boundary conditions which are slightly different from what's in the literature, or some literature. And we know the effective theory. So, and we know that there is some potential for getting baryons because we have something that we can identify with baryon number density. So now one has to run some consistency checks and see if one lands on one's feet. So the theory on the boundary is called the Floranini-Jakiv model. It's a theory of a chiral compact scalar. And there is a particular state or a vertex operator in this theory that has baryon number 1. So that's the formula for those who know. And the only thing that I've done is to try to compute its spin and energy using the technology of Chern-Simons theory with the boundary, and you get precisely what you expect, precisely n/2, which is the expected spin of that baryon. I have a slide that you might already have forgotten here, where I said that it would be important to keep in mind that for one flavor QCD, the spin of the baryon is n/2. And miraculously, from this complicated construction, that's exactly what comes out. Furthermore, you can compute the energy. That's given in terms of n divided by the size, the typical size of this sheet with a boundary. And the typical size of this sheet with a boundary can be obtained by balancing the tension force. So the sheet wants to shrink because it has tension, but now there is some degree of freedom on the boundary, which is excited. And that leads to some energy functional that's approximately like that. And this has a minimum when the size of the sheet is approximately 1. And so the baryons have the phenomenologically correct typical extent, which is the QCD size. Now, these are some consistency checks, not too many. It becomes much more impressive if you go to an f bigger than 1. As I told you, we can try to describe using this machinery also baryons with more baryons of high spin in QCD with more flavors. Let's say 3 flavors or 2 flavors. So one runs the exact same logic, but now the Chern-Simons theory on this sheet is non-abelian. One has to repeat the same computations, and amazingly, the spin comes out to be exactly correct, but also the isospin now comes out to be exactly correct. So the isospin is the new consistency check because there is no isospin for one flavor QCD, but now there is isospin, and the representation of this boundary excitation that carries baryon number 1 is exactly the right one. And the size of the baryon comes out to be correct, and the mass of the baryon comes out to be correct. So all the basic phenological properties come out to be correct. Or in other words, in this picture, what the baryons are, they are the following. Let me just try to explain intuitively what one finds. So in this picture, the baryons are like made out of these sheets, which are extremely long-lived, and you turn on some excitation on the boundary. And it turns out that this excitation carries the exactly correct quantum numbers. And it looks like a particle, like a big fat pancakey-like particle. Whether or not baryons look like that, it's an open question, these high-spin baryons. But they might as well they might look like that because they have a high spin. So many people have expected in nuclear physics already in the 70s that they will be flattened out. The thing that's weird about this picture is that it's not entirely consistent with the quark model because there is an interesting phase of glue inside this baryon, which is a topological quantum field theory. If you've ever looked at the constituent quark model, it doesn't really admit objects with fractional statistics. But since this is like the fractional quantum Hall effect inside this sheet, it goes beyond what the constituent quark model. Doesn't mean that it's wrong or right, but it is not entirely consistent with the constituent quark model. Okay. So As I said, people in nuclear physics have expected, based on phonological grounds, that the baryons with a high spin, since they have strong spin-spin and spin-orbit couplings, they would be flattened. Okay. So let me just summarize, so that I stay. So we propose that the QCD in the large N limit admits some new objects which are exponentially long-lived and they have a non-trivial topological field theory. Now, how did I argue that these objects exist? I cannot prove that they exist, but the argument was that we've constructed it as a composite object made out of an eta prime defect, together with the ordinary domain walls that are known to exist in pure Yang-Mills theory. And since when they get close, there is no reason to suspect anything other than that they would just combine, this looks like a natural conjecture. And as I said, it has been already confirmed, though not published, in the Witten-Sakai-Sugimoto model. Since this object is very long-lived, but not infinitely long-lived, one has to understand what happens when there are boundaries. And here there is a natural boundary condition to pick, which leads to particles, particle-like objects, which furnish the representations of QCD, which is non-trivial. And this leads to baryons which are naturally fast-spinning. Their spin is of order n. And some of their phenomenological properties that are easy to compute agree beautifully with QCD. Now, this model is probably complementary to the Skyrmian model. It does not contradict the Skyrmian model. It's probably complementary. And probably this model makes most sense at large spin. Let me just go over some open questions, and then we'll discuss if there are any questions from the audience. It's not clear if this agreement between the quantum numbers is a coincidence. It's not clear if baryons really look like that. It's an open question. It should be addressed by holography or the lattice. One can try to make contact with phenomenology, try to understand if these sheets actually exist in real QCD. And there are generalizations to many other gauge theories. In fact, one of the most interesting applications that I have no time to explain is to nuclear matter. It's been known for a while that at high chemical potential, at high density, eta prime becomes light, even in real life QCD. And these sheets have been discussed in the literature. These sheets where eta prime winds around some circle, around its target space circle, have been discussed in the literature in applications to various questions in neutron stars. But people have completely missed the fact that there is a Chern-Simons field theory on these sheets. And instead, there were some roundabout arguments with anomaly inflow about some excitations on the boundaries of these sheets. So I believe that this will, in fact, streamline a lot of the discussion of the properties of these sheets at finite chemical potential and some anomaly inflow that was discussed extensively in the literature. And it might be that, there will be some interesting applications to this field. Okay, now if there are any questions, yes, please. Yeah.
Is there any interesting consequences of the fact that actually, because of anomalies, the eta prime is not massless? I mean, I know you're at large n, but
Yeah, this is at large n.
Yeah, so it's somehow subleading, but still maybe there's some nice.
The anomaly that you are talking about is exactly what leads to this thing. Yeah. So in fact, you could say that the whole thrust of what I was explaining is due to this non-differentiable contribution to the eta prime mass, which comes from the anomaly. So yeah, so it's really the U1 axial anomaly that's responsible for this non-trivial effective field theory on these D2 branes in QCD.
Yeah. Even though somehow the shift to the mass kind of doesn't matter.
What's important is that the induced mass for the eta prime particle leads to a non-differentiable function on the target space. That's the most important, Sorry. Yes?
Can you imagine any way of relating the tension of your sheet to the QCD string tension?
Right, so I haven't explained that.
Quantitative prediction for the baryon mass? Like, let's say with one of these classical solutions with a
Yes.
long tube that's,
Yeah, I skipped over all these details, indeed. Let me try to so you can think, if you think about this sheet as made out of, one way to think about this sheet, which is sort of constructive, is as made out of as a compound object between the closed string domain wall that interpolates between these different instanton vacua and the eta prime defect. This part of the tension is calculable. It's just a problem in Sine-Gordon theory. You just take this effective field theory and you try to ask what is the energy of some kink. That's trivial. This scales linearly in n.
Yeah, I understand the scaling with n is fine, but there's a scale associated with the tension of this 2 plus 1 sheet. I'm asking if there's a relationship between, you can imagine establishing a relationship between the tension of this 2 plus 1 sheet and the 1 plus 1 QCD string. So that you might be able to,
I see.
Prediction, the baryon mass divided by, the slope of the leading resonance vector or something.
I see.
Equal to some number. And
I see.
The usual way that, we can see strings from brains,
So yeah, I can say something about it. Right. So I can say something about it. First of all, in holography, it's computable. All these numbers are computable. But one thing to say is that the total tension comes from combining these two things to first approximation. And I think it's correct at large n because there is the open string and the closed string sector don't talk to each other. So this part is easily calculable. And this part is not. This part is like the tension of this D2 brane in pure Yang-Mills theory. Now, however, that's just one number, and it has a fixed ratio to the string tension. So that can be measured numerically, and it was measured numerically by Tepper. So, and this is in fact gonna. So the short answer is that using one thing from the lattice, we can say I can sort of predict the ratio of the tension of the sheet to the string tension. It just requires one number that Tepper and his group computed already. So yeah, so I can relate this to the string tension. I haven't done that, but yes. And the most important thing is that the n scaling works correctly, and the baryon is of size of order 1. So of course, when the baryon is of size of order 1, you cannot compute anything, like in the Skyrmion model. So what people ordinarily do is they consider solutions which are not actual solutions, but they are much bigger, and they compute whatever they can in some regime which is not physical. And then they just hope that the results can be continued to the physical regime.
If I could just ask one very quickly, what I was wondering, instead of taking it from the lattice, can't you find a solution where you take the two-dimensional sheet and you tug on it, right, to something far, far out, so it looks like a classical solution, which looks like a long thing that then melts into the brain, and use that to separately determine the tension of the string when it's long.
I understand, but yeah, I understand. I don't know how to do it. I don't know how to do it in this theory, but there are papers of, let's say, Schiffman, who have added additional fields, drive the theory in some weakly coupled phase, and then you can compute whatever you want. But I wouldn't know how to do it in this theory without the lattice. Yes.
These sheets exist in Euclidean space and pure Yang-Mills theory.
I mean, Minkowski space. I haven't used Euclidean space at all.
You haven't, but if you go to Euclidean space, which the lattice does, these sheets still exist.
Yes.
And they're what, boundaries between changes in FF dual?
Yes. They would. Yeah, you could. I mean, one day, maybe in the 21st century, I hope that this would be seen. I mean, some parts of many ingredients in this story are extremely likely to be correct, or bound to be correct even. For instance, this part of the story where there is a sheet, a D2 brane. Sorry. This part of the story where you just take pure Yang-Mills theory without the eta prime, and you observe that there are these instanton vacua which are metastable. The picture is that the potential of pure Yang-Mills theory is like the true vacuum where we live, but there is also a vacuum where the instanton density is non-zero, which is slightly above. So this is supposed to be maybe order 1, but the barrier is maybe order n squared. So this metastable vacua should exist, and they should be one day seen on the lattice. And this object, which I call dW here, separates them. So this is like an object in space which interpolates between these two extremely long-lived states. And the fact that it has a Chern-Simons field theory living on it can be derived from anomalies of a higher symmetry, or at least motivated very strongly from anomalies of a higher symmetry. So I do expect that this exists, and it should be visible on the lattice. I don't know how is it going to be?
The reason I'm asking is that I think claims have been made like this on the lattice, which I have basically ignored. And the argument has always been whether they exist in the continuum limit or whether they're just lattice artifacts. You would say they would exist in the continuum limit.
They must exist. If what we know about Yang-Mills theory is correct, these objects must exist. And the eta prime sheets that I talked about must exist. And their bound state is likely to be what I said, but yeah, that part I cannot prove. So it's extremely likely that these things actually exist. But I don't actually know how hard it's going to be to see them on the lattice.
Well, as I say, some people I think have claimed to see such
Yeah,
things that
yeah.
have generally been ignored by the rest of the lattice community.
Yes, I understand. Any other questions? Okay.
All right, if not, let's thank Zohar again.